Okay, so now we're ready to move on to consider a component that is nonlinear, the first time we've done that, and that component is the diode. And so I've drawn the schematic version of the diode there. We also call the diode a p-n junction because it comes from combining two bits of semiconductor, one of which is p-doped and one of which is n-doped, and the interface between those two regions gives the diode its property. The diode has a cathode, given by the line here, which emits electrons, and an anode which emits holes or has little gaps for electrons, which is what we mean by holes. This is the anode, this is the cathode, and so the current, if it flows, will flow this way. When we forward bias the diode, meaning the voltage over here is higher than the voltage over there, then a current will flow in the direction of the arrow of the diode. So think of the black triangle as an arrow that tells you which way the current will flow. However, if we try to get current to flow backwards by making the voltage on this side higher than that side, we will not get any current to flow. And so we can actually write down pretty well what the current versus voltage for this is, and it's given in the graph here. So here's the voltage applied, here's 0, and so if we apply a positive voltage, so plus greater than minus, then eventually a current will flow, and if we apply a negative voltage, almost no current will flow. And in fact, we use this formula. So here's the current that flows based on the voltage applied, and notice that it's exponential, and so the more voltage we apply in the forward direction, when little v is positive, the more current will flow. That gives this exponential rise here. Notice that if the voltage is 0, the exponential gives 1, and we have 0 current flowing, as you would expect. And that if the voltage is negative, basically this term becomes very small, and we just have I naught times minus 1 in the negative direction. So I naught is a very small number which governs how much backward current will flow. Notice that there is a kT here, so that it's governed by thermal properties. KT is Boltzmann's constant times the temperature. And then there's a little factor of n that controls how quickly this exponential grows. And the charge of the electron is there as well. So for a typical silicon diode, the backward current is 10 nanoamps, or a very small number of amps, 10 to the minus 8. N is a factor of 2 for silicon, smaller for germanium diodes. And we can combine Q and NKT, oh, not the N, but the Q over KT, into something that has units of voltage, and that gives you what's called the thermal voltage. And this is a good number to memorize. The thermal voltage, I've written it here, is 25 millivolts at about room temperature, a little lower than room temperature. It's 26 millivolts at room temperature. So you can easily calculate the rise of this. If you know the thermal voltage, just remember 25 millivolts. So that if V itself is, say, 50 millivolts and we use 2 for N, then we have e to the 1 there. And you have to get a big number so you can figure out how much that should be. So, again, exponentials are nonlinear, and now we're dealing with a nonlinear circuit element, so we should emphasize that you cannot use superposition, and you cannot have a Thevenin equivalent of any circuit that involves a diode. And that is a problem because we use those implicit linear things for a lot of our circuit design. However, notice you can do the Thevenin equivalent for everything but the diode sometimes, and we can use the node method still, and so we can do a node analysis for the simple circuit shown here, where we want to know the node B here. we can do node analysis there. So the current flowing in through the resistor is equal to the current flowing out through the diode. That's my equation there. And then I plug in what those things are, the voltage across the resistor, so V minus VB over R. And then I plug in my IV characteristic for the diode, which I gave on the last page. That's given here. And I'm going to assume that I can neglect the 1 here because this is going to be much larger. And so I get this fairly simple equation. Now, I can't solve that equation by normal means. I probably can solve it. It probably involves a natural log, but I want to illustrate how you solve it graphically. So I have two sides of my equation. Here I have a linear side with a minus V d, so I'm going to get a negative line if I plot this side versus Vd. And on this side I have an exponential of Vd, so I plot those two things. So the blue lines here are the left-hand side with various values of R. In particular, I picked my input voltage to be 5 volts, and then I have 50 ohms, 100 ohms, 200 ohms, 500 ohms, and 1 kilo ohm as the lines I draw. And then I draw the exponential here as the exponential there. On this scale, I can only see it leave the axis about here, but in fact it's continuing down in its exponential way. Note that all the crossings happen in this little band right here, and that's very characteristic of when you're doing things with an exponential. In fact, I can increase the scale. I can, the bottom part, now I'm only going up to a current of 10 milliamps. This line moved over just a little bit, and you can see that now I have still my slopes. In fact, I increased all my resistors by a factor of 10 as well in this. So since the voltage of those solutions was mostly independent of anything else, we can imagine making an ideal diode that just turns on and off at a given voltage. So for a silicon diode, we might say that if V is less than 7/10 of a volt, we get no current flowing. That includes negative values. And that if the voltage tries to be greater than 7 volts, we actually just get 7 volts and the current flows. And so we draw that with the red line here compared to the yellow line of the actual figure, and you can see they do pretty well. An ideal diode we draw like this. It has a clear inside. We just draw the frame of it. And we either say the diode is off, meaning no current is flowing and a voltage less than 0.7 volts develops across it, or it's on and no voltage can develop across it, but any current can flow. So it acts like a voltage supply here with 0 volts, and it acts like a like a turned off current supply here, in other words an open circuit when it's off, and when it's on it acts like a voltage supply of 0.7 volts independent of the current that flows. Sometimes this 0.7 is also and we can talk about an ideal diode where it just turns off and on at 0. So current will flow one way but not the other. That's what we often think of the way diodes act. Current will flow this way but not that way is just saying that it turns off and on at 0 volts. And so with either of these, just the ideal diode with the break at 0.7 volts or the break at 0, it's piecewise linear, and so as long as we stick within the regions where it's on or off, we can use superposition and Thevenin equivalent in that case. And so I have an example to work through here. So we consider this circuit It has a voltage in and a voltage out, and it has an extra little voltage supply here to make things interesting. We have two ideal diodes, D1 and D2, and various resistors connecting them. And we want to find V out as a function of V in. So first consider the case where V in is less than 0. And in that case, this first diode, well, is off, and therefore I just take that whole part out. And the second diode, which was up here, is on because it allows the current to flow this way. And so I just have a voltage divider now where I have that the voltage out is 0.5 over 2 kilo ohms, so it's 1/4 of V in. But remember, V out has to be, or V in has to be negative, so V out is also negative, meaning this side is lower than that side, and the current flows like this, because there was a diode there, remember. So now, in between 0 and 2 volts, 2 because of this 2-volt battery that was there, neither of them's on, and just V out equals V in. If I don't include anything there, this 1.5 K doesn't matter. And we have that circuit. Finally, if this is higher than 2, then current can flow this way, because this is bigger than that. So current can flow this way through that, and then I can calculate V out again just by having things flow this way. And so it's easiest just to take, this point as ground, in which case I just have a 1.5 over 2, 2 times 1.5 voltage divider. So in other words, I take V in minus 2, right? That's the difference between here and here, and V out minus 2, that's the difference between there and there, and write that. So V out minus 2, here's my voltage divider compared to V in minus 2, and if I rearrange all the figures there, I get V out is 1/2 of V in, 1/2 from this, but shifted by 1 volt, the combination of all those constants. Plot that, and it looks like this. So in my 3 sections, I, in each case, get a linear behavior.